Previous class, we have seen the two-body problem reduced to one-body problem. In this lecture, we are going to see the equation of motion under central force and first integral. We restrict ourselves to conservative central force. That is where the potential is V of R, a function of R only, so that the force is always along the direction of R. In my previous lecture, that is two-body central force problem, we have seen that the problem of two-body central force reduced to a problem of single particle of mass m moving about a fixed center of force, which will be taken as origin of the coordinate system. Since potential energy involves only the radial distance, the problem has spherical symmetry. That is, any rotation about any fixed axis, that is more important, about any fixed axis can have no effect on the solution. Hence, an angle coordinate representing the rotation about a fixed axis must be cyclic. You have to note the point fixed axis. So, we will see what is fixed axis. Uh, and along particular axis only, this angular coordinate is cyclic. We are going to see it now. These symmetry properties result in considerable simplification in the problem. Since the system is spherically symmetry, the total angular momentum vector L is equal to R cross P is conserved. Don't confuse this L. This L is angular momentum operator. We use uh, customarily we use the L for Lagrangian operator also. Now in polar coordinate, the Lagrangian operator, which is equal to the kinetic energy minus potential energy, is equal to L is equal to half m r dot squared plus r squared theta dot squared minus v of r. This is the first two term. This is kinetic energy and this is potential energy. In this case, just now we have we know just I have explained that theta is a cyclic coordinate because it's a rotational spherically symmetry. This is since it's a spherically symmetry, it's independent of theta. So theta is a cyclic coordinate whose corresponding canonical momentum is angular momentum of this system. That is p theta is equal to partial derivative of Lagrangian with respect to theta dot. Here you can see the only this term, of course, with the multiplication factor of m is depends on the theta dot. So now if you differentiate this theta dot squared, you will get 2 theta dot. 2 will get cancelled. So you will get m r squared theta dot. Just now we have seen the P A theta is equal to delta L over delta theta dot, which is equal to mr squared theta dot. One of the two equation of motion is then simply uh, P theta dot. See, you can use the make use of the Lagrangian equation. We have just now seen there is no theta dependent in the Lagrangian, so the second term will be zero. Then only the first term left out, which is equal to the first term dl over theta dot is equal to uh, p theta. That means T by T of P theta is equal to P theta dot, which is equal to T by T of this one, M R squared theta dot, which is equal to 0 according to Lagrangian equation. uh, with the immediate integral, that is first integral of motion. This one is called first integral of motion. If you integrate it, only when you integrate a constant you will get 0. So that means m r squared theta dot must be equal to some constant. That constant is L. That is m r squared theta dot is equal to L. We are getting this after first integral. So this is the first integral of motion. We will also see the second integral of motion using the r coordinate. Before that, we will find some interesting thing about the proof for Kepler's law using this equation, that is by equation of motion, first integral of motion. Uh, Here, as I said, L is a constant of magnitude of angular momentum. So, from this equation, it follows. Uh, see, here we have seen uh, m r squared theta dot is equal to L. If you bring this m right hand side, L also constant, m also constant. If you differentiate r squared theta dot, that is left hand side. Right hand side naturally, because both are L by m is constant, it will be 0. So that's what I have written. T by dt of r squared theta dot, because m I have brought to the right hand side. Uh, r squared theta dot. Remaining term is r squared theta dot, which is equal to 0 if you are differentiating. Here, I have introduced of. Of is a scaling factor only, just a scaling factor. Uh, because of r squared theta dot is just the aerial velocity. That is velocity, the area swept out by the radius vector per unit time. This is the radial vector. In the given figure, uh, you can see the differential area swept out uh, in time tt being the small area ta is equal to of r, this distance, radial distance, uh, that is length into breadth. Here breadth is r d theta. So r d theta of r into r t theta, which is equal to r squared t theta. Hence, if you take time derivative of this small area, ta by tt is equal to 1 over 2 r squared t theta by tt. So, uh, the conservation of angular momentum is thus equivalent to saying the aerial velocity is constant. That is, here we have a proof of the well-known Kepler's second law of planetary motion. That is, the planetary motion covers equal area at equal time interval. The radius vector swept out equal areas in equal time. This is the Kepler second law. This is the proof for Kepler second law. Here you can easily understand. See, this is approximately taken when r theta is small, it is length into breadth area divided by 2, because if you add another area like this, it will be, this is half of the actual area. If you take rectangle, it is half. It is a triangle. So this is equal to half r squared t theta by dt, which is a proof for Kepler's second law. Just now we have seen the equation of motion based on the theta dot. Now we are going to see another equation of motion, which depends on the r coordinate. That is Lagrange equation for r coordinate is d by dt of delta L over delta r dot minus delta L over delta r, which is equal to 0. Now you see delta L over delta r dot. I have written in blue color font. So here, if you look into this Lagrangian equation, there is only one term which depends on r dot. That is first term of m r dot squared. So if you differentiate the r dot squared, you will get 2r, sorry, 2r dot. So 2 will get cancelled. This will become m r dot. Then next term minus TL over TR. Here two terms contain R, that is the second one, of M R squared theta dot squared minus V of R. So first you differentiate the second one with respect to R, then this will become uh, 2r theta dot squared. So 2 will get cancelled. Here there is one m. So this will become m r theta dot squared. Of course, the third term minus delta v over delta r according to this Lagrangian equation. Now you can write delta v over delta r as minus f of r. So you can rearrange the term t by t of m r dot is equal to m r double dot. This is that is a second derivative minus m r theta dot squared, this term. Then this is minus of minus will become plus. Already one minus outside the bracket, so this will become minus f of r, which is equal to 0. Or m r double dot minus mr theta dot squared is equal to f of r. Just now we have seen m r double dot minus m r theta dot squared is equal to f of r. Uh, Already we have seen in the first integral of motion as m r squared theta dot is equal to L. Then which implies theta dot is equal to L divided by m r squared. Substituting this in the above equation, that is this equation, because our ultimate aim is we want to find the equation of motion with the r coordinate. Earlier we have find the equation of motion based on theta coordinate. So we have to replace theta dot by r, that is r coordinate. So this will be equal to uh, first term we are taking as it is m r double dot minus m r. Instead of theta dot, I am replacing L by m r squared power whole square. Now, which is equal to f of r. Now you simplify this second term. L squared, which is equal to, in the numerator you have L squared, in the denominator m squared r power 4. This m squared will get cancelled with this m, you will get m. This r power 4 will get cancelled with this r, you will get r cube, which is equal to, originally we have defined f of r, that is minus tv by tr as f of r. Here you remember we have replaced partial derivative into full derivative because it depends purely on r coordinate. So partial derivative will become full derivative. That is easily you can understand. Now m r double dot is equal to L squared. This you are keeping to the you bring this to right hand side. This will become L squared mr cube minus, of course, delta v over delta r. This we can write 1 over minus 1 over 2 t by tr of L squared, because we have changed all partial derivative into full derivative because it depends only on r. So uh, this can be written as first term can be written as minus of t by tr of L squared over m r squared. Uh, if you differentiate 1 over r squared, here only variable is r squared, all are constant. If you differentiate r squared, you will get minus r cube. So this is minus r cube. Uh, so that minus I have put here because here you have plus, that become minus, and this r squared 1 over r squared, if you differentiate you will get to 2 divided by r cube. 2 will get cancelled, so naturally this will become r cube, that is L squared r cube, L squared mr cube. If you differentiate this L squared mr cube, then you will get this thing. You can easily verify this. This is equivalent to this one. Simply because the fact that if you differentiate the 1 over r squared, you will get naturally minus 2 divided by r cube. So this is equal to this. Here already there is a minus sign here. Uh, of course, I am sorry. We can take this. We are taking this. So this is equal to this term, this first term. So this you can easily understand. See, if you differentiate 1 over r squared, you will get minus 2 divided by r cube. Minus of minus will become plus, and r squared will become r cube. Exactly this term. So if you differentiate and use the scaling factor minus of, if you differentiate with respect to uh, r, then you will get exactly this. There is no difference between this term, and here this first term. Here this first term. That is this entire term. I will use different color this term. There is no difference at all. So the second term we are keeping as it is, minus dv over dr. So just now we have seen m r double dot is equal to half minus half d by dr of L squared over mr squared minus dv by dr. So here also you have minus d by dr, here also minus d by dr. You can take minus d by dr outside, then you bring this half inside, so this will become half L squared over mr squared plus b, because already we have taken minus outside. Now what you are going to do is you multiply uh, both side by r dot. So this side you multiply with r dot, and here also r dot. I have written this r dot as dr by dt. So what will happen? This is equal to of uh, m r dot square. If you differentiate this, what will happen? You will get 2 r dot. So 2 will get cancelled. If you differentiate this, you will get r double dot, which is exactly equal to m r double dot. Here, in same way, we are multiplying by uh, r dot dr by dt. Just some mathematical tricks. You take this bracket term as g. So d by dr of g of r, this entire thing in this uh, bracket, inside the bracket, is considered as g of r. This that is, you can see this two term we are taking as g. So I will use different color. This is g. Sorry, I will use a different color. Uh, so this entire term is g of r. Is g of r, and I am multiplying by tr over t. So, what will happen? This is equivalent to TG over TR into TR over TT, which is exactly equal to TG over TT. So, this bracket term automatically comes. This minus T by TR, TR by TT is equal to T by TT from this basic mathematics. So minus t by dt, I have taken this bracket term, that is of L squared over m r squared plus v. Now we got the expression finally. So you can see here also time derivative, right hand side also time derivative. You can bring both to the left hand side. So d by dt is of m r dot squared. This minus will become plus of here because we have taken d by dt outside. This minus will become plus when you are bringing to left hand side is equal to of L squared over mr squared plus v, which is equal to 0. If you take, if you differentiate a constant, then only it will be 0. So if you integrate it, that is first integral, you will get the terms inside the bracket. That is this term, these three term you will get, which is equal to a constant e. This is equal to a constant e. That's what I have given here. So, of this is first integral. If you integrate it, of mr dot squared plus of L squared over mr squared plus v is equal to e, which is a constant. Uh, this e is the total energy, which is a constant, by from the basic mathematics. This is a statement of conservation of energy, and this is another first integral of motion. We have already seen one integral of motion using theta coordinate, that is m r squared theta dot is equal to L. Here is the another one. This is about the first integral and for the central force field. Thank you very much for watching my videos and supporting me continuously. If you have any question, kindly send to the following mail ID wasimku@gmail.com. I will answer earlier through mail or YouTube videos. My YouTube channel ID is youtube.com/at vasuvphysics. Thank you very much.